my name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on exam papers. And this exam paper we're going to look at is the OCR June 2013 F322 or Unit 2 past paper. Now the whole point of these videos is to go through each question and show you some example answers that you could write, and we're going to go through the marking structure as well. And the whole point of these videos is to basically address a concept called exam technique. So it's one thing that you know the content, you can read the book and remember the content, but it's completely another thing applying that content to an exam situation. So the whole point of these videos, like I say, is to address that. Now, it would be a good idea to see if you can try and get a hold of these papers here. These papers are readily available from the OCR website. You can write your answers to them, and then you can look back through this video, and I'll go through the answers and give you some hints and tips along the way to help you be successful in answering your exam paper. Also, you can go straight to a specific question if you like. If you just click on the links to the left-hand side, on the screen there, you can jump to any question you want in this paper, so you don't have to go through the whole thing. Okay, right, let's make a start. So we're going to start with question 1, and it says crude oil is a complex mixture of many hydrocarbons. Crude oil is processed by the petroleum industry to make fuels and petrochemicals. The straight chain alkane A is present in crude oil. A has molecules with 10 carbon atoms. What is the molecular formula of A? So the molecular formula would be C10H22. So it's an alkane, so it's going to be CnH2n plus 2, which is going to give us H22. Okay, so and then it says B is a branch chain isomer of A. Draw the skeletal formula, so that's really important, of a possible structure for B and name your structure. So they want just skeletal. They don't want any displayed or structural. It's got to be skeletal. So it's branched. You can have loads of different types. I'm just going to draw one out here. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you can have a methyl group hanging off the second carbon. So that one would be something like 2-methyl non-in, because we've got nine carbons in there. But anything that's branched and has the same formula of that, then that'll do. They'll accept either of them, obviously. So that's just an example there. So this is 1 mark, and so is that one. So you get 2 marks in total there. Okay, so not too bad. And on to the next question. It says the branch chain isomer B has a lower boiling point than the straight chain alkane A, and we've got to explain why. Okay, so we've got to say basically that what actually governs boiling points in alkanes is the intermolecular forces between the chains. And in this case, it will be van der Waals forces. If we have branches coming from here, then the chains can't pack together as closely. And that actually means that the van der Waals forces is reduced dramatically because we can't compact as many of these together. So what we need to say is that B, which is the isomer, has less surface contact between chains. So, like I said, that means we have less van der Waals forces. Okay, right, and so that'll be your first point, and then we need to say, because it does say explain, so we've got to say what effect that has, and the effect is that less energy is needed to break intermolecular forces. All right, okay, so we get 2 marks for this. So the first mark comes in by saying that B has less surface contact between the chains, or anything along the lines of they can't compact as much together. So we have less van der Waals forces. That is really important. And And so there's your first mark, and then your second mark is explaining obviously the effect of that. And so less energy is needed to break the intermolecular forces, gets you the second mark. So it's really important that you bring it back full circle. Okay, right. On to the next question, which is this one here. And so it says, a chemist heats a pure sample of C15H32 in the presence of a catalyst. A reaction called cracking happens. Construct an equation to show the cracking of C15H32. So again, this could be anything, but when we do cracking, then we actually get an alkane and an alkene. So we're going to start with C15H32 because that's what we're starting with. And you could form any alkane and an alkene. So I'm going to say that my alkene would be C2H4. And then you just see how many carbons you've got left. So that's going to be C13. And how many hydrogens we've got left would be 28. There you go. So there's your alkene and there's your alkane. As long as you have these, an alkene and alkane, and the number of carbons and hydrogens add up to the original alkane, then you should get the mark there. Okay, and then the next one, it says, when cracking takes place, a large number of products is formed. Suggest why a large number of products are formed. The key thing is because the carbon chain, anywhere along the carbon chain in here, would actually could actually break. So that means we get loads of different types of hydrocarbon produced, loads of different chain lengths. So that's the key reason. So it is just one mark, so we don't need to go into a lot of detail here. So the carbon chain can break in many different places. All right, okay, so there's our mark there, or anywhere where you can say that the carbon-carbon bonds can be broken anywhere along that chain, and that gives us obviously the variety. All right, okay, on to the next question, or the next part of the question. Okay, so we've got part C, and it says the petroleum industry processes straight chain alkanes into cyclic hydrocarbons. For example, octane can be processed into a cyclic hydrocarbon and hydrogen. Suggest the structure of this cyclic hydrocarbon. So I suppose the most obvious one is you've got octane, which is 8. So we have cyclooctane, which is just an octagon. So we can draw it like this. So we have 1, 2, 3, 4 carbons, 5, 6, 7, and then your 8th one. And then if we join them up, there you go. Okay, so we've got 8 different carbons that's dotted around there, and this is cyclooctane. You could go for, if you know this, you could go for an aromatic compound, although this, probably a lot of you might not know what this is, but it's just an alternative answer, where you can have something like this, which is 1,2-dimethyl benzene. But yeah, anything like that. This is probably the most obvious one, though, that you would probably draw. Okay, and that gets you the 1 mark. And then the last question, it says, why does the petroleum industry process straight chain alkanes into cyclic hydrocarbons? There's a load of different answers for this, but basically, cyclic hydrocarbons increase the efficiency of combustion engines. So we'll say something along the lines of, so combustion efficiency increases using cyclic hydrocarbons. Go. So you could say anything to do with increasing the octane number, cyclic hydrocarbons reduce knocking. You could say that cyclic hydrocarbons are more efficient fuels, or they burn better, or anything kind of along that lines. Then you would get the mark there. So there you go. There's 9 marks. Some hydrocarbons there, and a little bit of organic chemistry. On to the next question. Okay, so this is question 2, and it starts by saying the skeletal formula of 6 alcohols C, D, E, F, G, and H are shown below. You can see they've given us a range of different alcohols. So it says which 2 alcohols are structural isomers of one another. So we need to show the obviously the same molecular formula, but they are structured differently. So you can see here that we've got 1, 2, 3, 4, 5 carbons here, and this one's got 1, 2, 3, 4, 5 carbons as well. But this one is structured differently to this one. So they're the first two that you can see that are different because we've got a branch here and there's no branching here. So it can't be G because we've actually got a different functional group in there. So that wouldn't be classed as this molecule here. Even though it's got 1, 2, 3, 4, 5, the same number of carbons, it does actually have less hydrogens than either of these because of that double bond. So the answer would be E and H. Okay, so it then says which alcohol is a tertiary alcohol. So we need to look at these and we can see that actually H is the tertiary alcohol. This is the alcohol here and it's bonded to a carbon, and this carbon is bonded to 1, 2, 3 other carbons. So that's why it's tertiary. So that one's going to be H. Okay, it then says which alcohol can be oxidized to a carboxylic acid using K2CR2O7, which is potassium dichromate. So we need to look for an alcohol that is either, well, this has got a carboxylic acid, so it's got to be a primary alcohol, and the primary alcohol here is F. It's the only one that's primary, so this one's going to be F. Okay, and then it says the next question. It says what is the molecular formula of alcohol G? So if we go back, now you can see we've got 1, 2, 3, 4, 5 carbons there. So that's going to be C5. The number of hydrogens, we should have 2 hydrogens there, which is 1, 2, 3, 4, 5. And we should have 6, 7, 8, 9 there, and we should have 1 sticking out there, which is 10. So that's going to be C5, H10. And then obviously we've got our oxygen as well as part of our alcohol. So there's your answer there. All right, okay. And then the next one, it says, what is the name of alcohol C? So if I just scroll back up, there's alcohol C. So if we find our longest hydrocarbon chain, 1, 2, 3, 4, 5 carbons, so that's a pent. And off the second carbon, which is here, so that'll be carbon 1, that'll be carbon 2. We have a methyl group, and then off the third carbon, we have a alcohol, which is the OH. So in terms of nomenclature, this should be called 2-methyl pentan 3-ol. There you go, and that's the name of alcohol C. Okay, and the next part, so you get a mark for each one of them, and it says the alcohols are members of a homologous series. Explain the term homologous series. So homologous is a bit like the family. So for example, you might have different, for example, in a normal family, you might have, again, a human family, you might have, you've obviously got parents and then you'll have children as well. Now all the people in that family would have the same surname. And so, but each person in that family is slightly different. They have different characteristics, different personalities. So it's the same with chemistry as well. So when it says explain the term homologous series, we basically have the same functional group, which is like the surname, but they are different. And in terms of chemistry, they're different by CH2 each time. So it's a 2-mark question. So that's obviously the 2 points there. So these are basically, this is a compound with the same functional group. So that's the key thing, but we've got to say that each successive, that's really important as a term, successive member differs by CH2. All right, okay, so let's look at the points here. So we get 1 mark for saying what is the same about them, which is always the functional group, and then each successive member differs by CH2. So that's the only real difference between the two, and that's what we call homologous series. Okay, so you get 2 marks there. Okay, right, so on to the next bit. Now this is quite a big question, structured quite a lot. So we can see here we've got alcohol D is reacted with 3 different reagents. Complete the flow chart below to show the organic products formed in each of the reactions of alcohol D. So you can see here's alcohol D here in the middle, and we're going to heat first of all with acidified potassium dichromate. So this is an oxidizing agent, so it'll oxidize this alcohol here to a ketone, because this is a secondary alcohol. You can see we've got the carbon that's bonded to 2 of the carbons. So this is going to be oxidized to a ketone. So all we have to do is draw this product, except turn that into a ketone. So it's going to be 1, 2, 3, 4, 5, 6, 7. And then coming off here, we have a double bond O. Okay, so that's your ketone. All right. And it then says heat with ethanoic acid and an acid catalyst. So this is an alcohol and an acid with an acid catalyst. This is going to be esterification. So we're going to form an ester here. So again, we'll draw our product here, as this bit remains unchanged. So this bit here, we still have our oxygen there, but because it's an ester, we have a double bond oxygen there, and we have a methyl. So this is CH3COOH. So the ester that we're adding on here is the 1 and 2 carbons there. So you can see this is the 2 carbons, and then that's bonded onto the oxygen. And obviously you'll produce water as well as another product. All right, okay. And the last bit, which are these 2 boxes here, so it says heat with an acid catalyst. So we've got this molecule here, and we're going to add an acid catalyst and just heat it up. This is a classic example of condensation reaction or dehydration reaction. So this is where we're going to remove water from this molecule when we heat it with an acid, and so we're going to form these products here. So we're going to form this one first. And so what's going to happen is this OH is going to drop off, and a hydrogen is going to be lost from here. And so that's going to form a double bond in the middle, which is going to go there. And so there's your first product. But also, this OH could go, and this hydrogen could lose, forming a double bond there. So actually we get 2 different products being formed here. There. So there's our double bond there. So actually we get 2 different products there. Now for each one of these, we get 4 marks. Sorry, for each one of these we get 1 mark, but that adds up to a total of 4. So you can see here we've got 1 mark there, we've got 1 there, and then obviously we've got 1 there, and then 1 there. So that totals up to 4. So the total number of marks, as you can see, is 11 marks. 11 marks in total. So a lot of organic chemistry there. So make sure you're able to name your structures and identify primary, secondary, and tertiary alcohols as well as nomenclature. Okie doke. Right, on to the next question. Okay, so this is question 3, and it starts by saying that compound I is found in biodiesel, and it has the skeletal formula shown below. So we've got this very long molecule here. It says name the 2 functional groups that are present in a molecule of I. So you can see here that we have one here, which is an alkene. That's probably the obvious one, which is there. And we also have, you can see up here, we have a ester group, which is this group up at the top here. So you got the C double bond O, and then O, and then your methyl group at the end. So we also have an ester. All right, okay, so that's 2 marks. Now, that's quite obvious to break down, so you just get 1 for each. You get 1 for that one and 1 for that one as well. Okay, right, so on to the next one. It says, why is compound 1 unsaturated? And the reason why we can say it's unsaturated or monounsaturated, at least, is because it has this double bond here. And anything with the double bond is classed as unsaturated. So the word saturated is commenting on the number of hydrogens in the molecule. The more hydrogens you have per carbon molecule, the more saturated your molecule is. So having a double bond effectively removes some of the hydrogens from the molecule because the bond is taken up some of the space of the hydrogen. So what we need to say is it contains a CC bond. That's a double bond there. All right, okay. So on to the next one. So it says a sample of compound I is shaken with aqueous bromine. What what colour change would you see? This is the test for an alkene. So if we shake bromine water with this, there's your alkene there. What you should see is it go from like a browny orange to colourless. Okay, so that gets to that mark there. All right, and then on to the next question. It says compound J is a stereoisomer of compound I. What is meant by the term stereoisomers? Basically, it's the same structural formula. But we have a different arrangement of atoms in space. All right, okay, so that gets us 1 mark. So you've got to say same structural formula. You've got to say what is the same and then say what's different. So these are just where the atoms are arranged differently. Okay, and the next bit, which is part 2. So it says here, draw or describe how the structure of J differs from that of I. So we can say that J is a stereoisomer. So this is your EZ isomerism, as you may also know it as. Now you can see in this molecule, I'm just going to bring it down so we can see it. You can see there's our double bond. EZ is always around double bonds. And you can see our carbon groups are actually kind of bending up on the same way. Now here you would have 2 hydrogens. That would be down here. So you can see it bends up. So the isomer is where actually this carbon here would be down here. So it will be opposite. So we'll just draw that structure there. And actually all I want in the exam is for you to either draw the structure or describe it. And it's probably a lot easier to draw it. There you go. So there's your CH3 and there's your CH3. And you can see it's opposite the double bond. So we call that trans, or we can also call it E, or we can also yeah, they're the main 2. So you either call it E or trans, which means it's opposite, whereas this one is cis at the top. Okay, so that gets you that mark there. All right, okay, and then on to the next part. So this is part E, and it says a student determined the enthalpy change of combustion for compound I. In her experiment, 1.34 grams of compound I was used to heat 50 grams of water. The temperature of the water changed from 20.2 degrees Celsius to 54 degrees Celsius. What is meant by the term enthalpy change of combustion? We've got 2 marks here, so we're looking for 2 key things. And basically, this is a one that you've really got to remember, but it's the enthalpy change when 1 mole of a substance completely combusts. So that's really important because we assume, and it doesn't actually happen practically, but we assume that for the theoretical, that it completely combusts and all of the fuel is being used to provide the energy, and we don't have any incomplete combustion. So in this case, it's 2 marks. So you get 1 mark for saying the enthalpy change when 1 mole of a substance. That gets you the 1 mark, and then completely combusts, or you can say reacts fully or completely with excess oxygen. So you must have an excess of oxygen to have complete combustion. So yeah, that gives you the 2 marks there. Okay, so then it says calculate the energy released in kilojoules in the student's experiment, and the specific heat capacity of water is 4.18 joules per gram per Kelvin. Right, so the energy released, so this is your equation, and it's Q equals MC delta T. It's a bit like a DJ, MC delta T. And the Q will equal the mass, and the mass of the water. So when we're referring to the mass here, we're talking about the mass of the water there. So the mass is actually 50. We're not talking about the fuel. This is always the mass of the solution. The specific heat capacity is 4.18. And the change in temperature is 20.2, 54 degrees. So that's an increase of 33.8. It should be. Okay. And if we put that into our calculator, so what we should have, just stick it on that side there. So we should have 50.0 times by 4.18, multiply that by 33.8, and that should get us 7064.2. 7064.2. Now that's in joules. The answer said we needed it in kilojoules, so we moved the decimal point back 3 spaces to get into kilojoules. So that's 1, 2, 3. So that's 7.0642 kilojoules. And there we go. So in terms of marks, the number of marks would be 1 mark for this there, and then 1 mark for your actual final answer. So I guess the 2 marks. Lovely. Okay, and then part 3. It says the molecular formula of compound I is C17H32O2. Calculate the amount in moles of compound I by the student. So we have a we have a formula, so we work out the molecular mass. We also have a mass as well, so which was mentioned up here before, which I'll show you in a minute. So we need to work out the number of moles. So moles equals mass in grams over mR. So the mass, we were told that, if I just refer you back up to here, that we had 1.34 grams of the compound. So therefore, we're going to put that there, 1.34 grams. We're going to divide that by, now we have to work out the molecular mass of this. So carbon has got a mass of 12. So we're just going to put that into brackets. That's 17 times by 12, because that's the mass of carbon, plus 32, because that's the mass of hydrogen, or 32 hydrogens, that's just 1, plus, and then we need 2 times by 16, because that's your mass of oxygen, or the molecular mass of oxygen, and we should get a final answer of 268. So that's what we're going to divide it by. There you go. And then if we put that into our calculator, 1.34, divide that by 268, we should get 5 times 10 to the minus 3, as you can see on there. Okay, so minus 3 moles. All right, and so the number of marks that's available here, you get 1 mark for actually working out the MR of your molecule, which is 268, and you get 1 mark for actually calculating your moles as well. So there's your 2 marks. All right, and then for the next bit. So it says IV, calculate the enthalpy change of combustion of compound I. So the enthalpy change is, obviously enthalpy is delta H, and that's measured in kilojoules per mole. So that might give you a little bit of hint how to calculate this. So kilojoules is the energy, which we worked out there, and that was Q. And obviously this is the number of moles. So that's why we worked out energy in moles, you see. So the energy is in kilojoules. So this is going to be this number here. So that's going to be 7.0642. We're going to divide that by the number of moles that we had, which is 5 times by 10 to the minus 3. And if we put that in our calculator, so we have 7.0642. I'm going to divide that by 5 times by 10 to the minus 3. We should get 1412.84, but I'm going to round that up, so it's 1413. All right, now what's really important, a lot of people forget this as well, is actually this is an enthalpy change. Enthalpies can have a positive and a negative value. Because we're burning a fuel, this is combustion. Combustion is always exothermic, so therefore our enthalpy change has got to be exothermic. So we've got to include the minus on there as well. That's really, really important, because actually you get a mark for just putting the minus there. So, so in terms of the marking, we get 1 mark for actually doing this bit. We get 1 mark for our answer, and then 1 mark for the sign as well. So you get 3 marks in total there. That's really, really important. Don't forget that. If you're burning anything, it must be a negative value, because that shows it's exothermic. Okay, right, so on to the next bit. It's a big question, this one. Right, So part 5. So it says the student noticed that compound 1 burnt with a yellow flame and produced black smoke. Suggest an explanation for these observations. Whenever you see this yellow flame or a lot of soot being produced, this is a classic sign of incomplete combustion. Right, okay, so there's your answer. And part F, it says some scientists believe that we should use more biofuels such as biodiesel and bioethanol. Bioethanol is made by the fermentation of plant sugars such as glucose. Write an equation for the fermentation of glucose to make ethanol and state 2 essential conditions for this fermentation. So the equation is C6H12O6. That's your formula of glucose. And we are producing ethanol, so that's going to be C2H5OH, and we're also producing carbon dioxide as well. So we'll put that on there. All right, and so there's our equation. Now, obviously, we have to get this balanced. So in terms of the number of hydrogens, you can see here that we've got 12 hydrogens on this side. We've only got 5 on this side, so we need to multiply, well, 6, sorry, because we've got the hydrogen there. So we need to have a 2 here. That gives us our 4 carbons there. You can see that we've got 1 carbon here, so we need a 2 here as well. And so that will balance everything. Okay, and then we need essential conditions. Now, one of them is obviously yeast, or you could say zymase as well, so that's your catalyst that you're using. And another condition, because you're using yeast, one of the obvious ones is temperature. So anywhere between 20 and 45 degrees Celsius will do. Or you can say a lack of oxygen. So we don't need a lot of oxygen. So this is anaerobic respiration to produce ethanol. Or you can say water. So any one of them will do, and that will get you the mark there. So in terms of marking, we get 1 for our equation, making sure it's balanced as well. 1 for saying yeast, and then 1 for any one of these will get you that 3rd mark. So this whole question was out of 19. It was a big question. Some enthalpy changes there. You've got to make sure you know your calculations, and the units can help you to work out the equations as well. So for example, enthalpy change, the units is kilojoules per mole. So you know that to work out enthalpy change, you have to have the energy divided by moles. So that can give you a little bit of a hint as well. But that's it. On to the next question. Okay, so this is question 4. Question 4 says iodine monobromide, which is IBR, has a permanent dipole. Alkenes react with IBR in a similar way to the reactions of alkenes with HBr. Propene reacts with IBR to make 2 possible organic products. One of these products is 2-bromo-1-iodopropane. Using the curly arrow model, complete the mechanism to make 2-bromo-1-iodopropane. Right, okay, so this is for 3 marks. It's a standard mechanism. So you can see here that we've got an alkene. Now, the important thing is with mechanisms is that arrows always show the direction of electron flow. So they always go from areas of high electron density to low electron density. And in this case, we have a high electron density in our double bond there. So our first arrow is going from the double bond to the iodine, because our iodine is actually delta positive. Now, because this has formed a bond with the iodine, this bond has to break. So the electrons go from the bond, because that's where the electrons are, to the bromine, which has a negative charge anyway. So we've got this kind of like domino effect going on here. Okay, and then we've got to draw our intermediate and then show obviously what our product is there. So what's happening here? Now you've got to look very, very carefully because the iodine is added on straight away. But you can see the iodine has gone on to here, and then the bromine will add on at a later stage. So we've got to leave this carbon free. So it's really important to look at your product to make sure you draw your intermediate correctly. So we're going to draw our H, and obviously the CH, and the I has now added onto this side, and this leaves CH3. Obviously that hasn't changed, and then the hydrogen which is there, this leaves this for the bromine to add on at a later stage. It's got to be that carbon. If we did it the other way around, it wouldn't match the product there. So you'd actually lose a mark. So make sure you draw it in that particular way. We also have our bromine, Br minus with a lone pair as well. So there's our Br minus, and there's our our carbocation, we call this. So that's that one there. And obviously the bromine's going to add itself on there, but we need to draw another arrow to show this. So the electrons come from the lone pair to the delta positive carbon. You can do it from the negative charge to that as well, but make sure you're really specific to where you're going. You've got to be really, really specific. Just like with this one, the electrons are going from the bond to the bromine. It's not coming from the iodine. So if you're kind of sloppy with your arrows, and the arrows go in the wrong place, you'll lose the mark. So this is a 3-mark question. So you get 1 mark for actually both of these arrows here. You get 1 mark for drawing the correct structure with that positive charge in there as well. And you get 1 mark for this curly arrow there. So that gets you all 3 marks. Okay, right, on to the next question. It says, what is the name of this mechanism? Which is this one here. And the name of the mechanism is electrophilic addition. Now, the reason why it's electrophilic addition is because we have an electrophile here, which is our IBR. So this is the one that's attracted towards this high density area of electrons. So this is your electrophile, and we're adding it because we're adding something to the double bond. So whenever you see we've got a double bond and then we're forming a product that isn't a double bond, this has got to be addition because we can only add things to double bonds. So yeah, that's that answer there. Okay, and then it then finally goes on to say, draw the structure of the other possible organic product of the reaction of propene with IBR. So the other product, here's our alkene, which is here, and the other product is going to be where the bromine is going to be here and the iodine is going to be there. So it's basically just swapped over. So we've got hydrogen, we've got bromine, iodine, CH3, and hydrogen. Okay, and so there's your product. So you can see it's just back to front from there. So this is where the bromine, in other words, our carbocation is an intermediate, would actually be on this carbon here, and then the bromine would then add itself onto there. So that's how we would get that other product as well. Okay, right, next. So just put it down there. Right, so you see we've got B. It says methane reacts with IBR to form many products. 2 of these products are iodomethane and hydrogen bromide. It says suggest the essential condition needed for this reaction. So whenever we get a halogen reacting with methane and we're forming many products, then we know this has got to be a free radical reaction. And for free radicals to be formed, we need UV light. So that is the essential condition that we need. So we need UV. Okay. And the next bit. Okay, and this obviously leads us nicely into radicals. So the mechanism of the reaction involves 3 steps, one of which is called termination. Describe the mechanism of the reaction that forms iodomethane and hydrogen bromide. Include in your answer the name of the mechanism, the names of the other 2 steps of the mechanism, equations for these 2 steps of the mechanism, the type of bond fission, and 1 equation for a termination step. And the answer should link to the named steps to the relevant equations. So that's what we're going to do. Okay, so we're going to start with the name of the mechanism. So this is a free radical substitution. Because what we're doing is we're substituting a hydrogen in methane for an iodine, so we're swapping that, but we're forming radicals at the start. All right, so they've given us one of the names of the steps, which is a termination step, which was one of them there. So the start step, or the first step in any of these reactions, is called initiation. Now it did say in the last bullet point that in the second last bullet point, sorry, the third one, the third one from the bottom, it says equations for these 2 steps of the mechanism. So we've got to link the named steps here to the relevant equation. So that's what we're going to do first. So we'll start with initiation first. Now we'll start with IBR. There's our halos, our halogen molecule. So we're just going to put IBR there. And if we fire UV at it, we actually split it and we get two radicals formed. So we get an I dot and we get a Br dot. So there's our two radicals there. And this type of reaction is called homolytic fission. Homolytic meaning we are splitting it in the same, so equally. So one electron goes that way and one electron goes that way, and that's why we form these two radicals. And fission means to break, so we're breaking the bond. So this is called homolytic fission. And so that's the name of the mechanism. We'll do one of the steps already, and we've done the type of bond fission as well. So we've done that one there. Okay, so this is our first step. And then the next name of the step is propagation. So we'll put that there, propagation. Okay, so propagation means to allow the reaction to carry on. So it's like the intermediate steps. So there's our two names of our mechanisms there. And we have to write the equations for this one as well. So now the idea with propagation is that your product from over here, your radical product, will react with a non-radical, and that's always the case. It's always radical and non-radical. So we're going to start with this first, which is Br dot, which is this one here, and that's going to react with CH4. Because that's what we're reacting it with, is methane. And because you can see right at the top of the equation, it says methane reacts with IBr. So Br dot plus CH4, and that will form HBr plus CH3 dot. It's a little bit like pass the parcel, except this is like pass the radical. So the radical was on the bromine, and now it's been passed to the CH4, but the CH4 has to give up a hydrogen as part of it as well. So we know that we're reacting it with a Br dot because it says one of the products is hydrogen bromide, and there's our hydrogen bromide there. So we've made our product straight away, and we've formed a radical. So always, propagation is always radical and non-radical reacting together. The second stage of propagation is always the radical from the first one. So the first product here, always the radical, and this is always brought down to start the second stage. Now, ideally, we're going to form iodomethane. So we've got the methane bit there. So we need to react this with a molecule with iodine in. And that was the IBr that we started with right at the start. So we've always got radical and non-radical. You can see the pattern there. And we're going to form, basically say pass the parcel. So the radical gets passed over here and the iodine comes over here. So they're like swapping over. So this is CH3I. There's your iodomethane plus Br dot. And we know that the radical product here must be the reactant at the top here. So there's another checking point to make sure that it's correct as well. Okay, and there's your propagation steps, and this will carry on going until termination. Now termination is the there you go. So termination is the last process of this reaction. Now it did say that one equation for termination step. So there could be numerous ones here. All we have to do is just pick two radicals that we have floating around here, combine them together, and we form a non-radical, and that's all termination is. So for example, you could have I dot plus CH3 dot, and that will form CH3I. You could have Br dot plus Br dot, and that will form Br2. You could have I dot plus I dot, and that will form I2. You could have Br dot plus CH3 dot, and that will form CH3 Br. We could have CH3 dot plus CH3 dot, and that will form C2H6. And we could also have I dot plus Br dot, and that will form IBr. So do you know any one of them? You can see there's loads there which you pick from. It's just as long as there's two radicals that collide together, any one of them are termination reactions. Now, this whole question was out of 7, and it goes on to the next page as well, so they'll give you plenty of space to write it. So in terms of the marks, you actually get 1 mark for saying free radical substitution. You get 1 mark for saying initiation is one of the steps, and you have to link it with the equations. You have to make it really obvious. You get 1 mark for saying homolytic fission as well, 1 mark for saying propagation and linking it with the equations, and that gets you the other mark. And the final mark comes into writing any of these equations here. So you can see that we get a decent range of marks here. 1, 2, 3, 4, 5, 6, 7 marks in total. So yeah, that's the end of that question. Make sure you know how to do these. These are really, 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 really important. And just follow the little prompts as I've shown you just before, and you should be fine. Okay, on to the next question. Okay, so this is question 5, and question 5 is mainly concerned with energetics. So it says nitrogen forms several oxides, including N2O4, N2O, and NO. It says a rocket uses the reaction between N2O4 and methyl hydrazine NH3 NH2, equation 5.1, to release a large amount of energy. And it's given us the equation here. So it says some enthalpy changes of formation, delta HF, are shown in the table, and you can see that it's given us a load of formation data. Okay, so now what it's asking us to do is to use the enthalpy changes of formation to calculate the enthalpy change of reaction in equation 5.1. So I'm just going to nudge that up a little bit, just so we can see. Right, so we're going to start by doing what we call a Hess's cycle, and it helps us to calculate it. Now, the data they've given us is formation data, so we have to draw a Hess's cycle with our elements on the bottom and arrows that point upwards like that to our reaction, which is written down up there. So what I'm going to do is I'm going to write our reaction first, which is this reaction here. I'm just going to rewrite this out. So that's going to be 4 CH3 NH2 plus 5 N2O4, and that will produce 4 CO2 plus 12 H2O plus 9 N2. Okay, so there's our top line. So I'm just going to nudge that a little bit further forward so we've got space. So we need to write our elements here. So the elements that make up this include carbon, which is solid. We're going to have nitrogen, which is N2, and that will be in the gaseous phase. We're going to have hydrogen, which is H2, that's also in the gaseous phase. And we're also going to have oxygen, which is O2, and that's given the gaseous phase. So these are just elements in their standard states. We don't need to worry about balancing these to match these. It doesn't play any difference in the calculation, so we're just going to make it a little bit easy for ourselves. And because it's formation, we're going to say these are the elements in their standard states, and that's forming our reactants and products. And so we're just going to put delta HF, and same there as well, delta HF. And we want to work out this, which is delta H of the reaction. So all we have to do is work out the formation data. So they've given us the information here. So we need to work out the formation of this compound here first, which is your methyl hydrazine. And so this is 54, but we've got 4 of them. So we're going to do 4 times by 54. And if we put that in our calculator, it gets 216. There we go. And then we've also got 5 lots of N2O4. Now N2O4 is minus 20, so it's going to be 5 times by minus 20. Obviously that equals minus 100. And if we add them two together, we should get 116. Okay, so that's our total enthalpy of formation for our reactants. So now we need to do enthalpy of formation for our products. So you can see here that we've got 4 lots of CO2. So that's going to be 4 times by, now carbon dioxide is minus 394. So if we bring over our calculator, 4 times by minus 394, that will give us minus 1576. Okay, and we also have 12 times by, now this is water, the formation of water is minus 242. So if we put that into our calculator, 12 times by minus 242, that's going to give us minus 2,904. Now if we add all of them up together, so it's minus 1576 plus minus 2904. That should give us minus 4480. Okay, so that's basically our totals. Now at the N2 one here, you can see we don't have any data for N2 because we're forming it. The elemental state, what we started with, isn't actually any different from there. So the enthalpy change is 0 for nitrogen. So what we have to do is work out this value up here. Now, we can treat this like a roadblock. So we need to get from here to here because that's the root number we want to work out. But we can't go there. It's a bit like a blocked road. So we have to take a diversion. So we're at this point here. So we need to go against the arrow here and then with the arrow here to get to our product. So whenever we go against an arrow, we have to change the sign around here. So that's going to be minus, because we're going against the arrow, that's a plus 166. So that's going to be minus 116, sorry, which is on this side. And then we're going to do this one, and we're going with the arrow. So this is minus 44. So we keep the sign the same. Minus 4480. And if we press equals, and we should get that. Minus 4596. So I'm just going to put that in there. Minus 4596. And that is kilojoules per mole. Now you can see that reaction sensible because this is obviously rocket fuel, and you expect rocket fuel to be exothermic when you burn it, which is exactly what we've got there. So we get 3 marks in total for this, and the 3 marks come in by working out this one, working out this one, and working out obviously your final answer, and that's where you get your 3 marks. So very exothermic reaction, incredibly exothermic actually. Okay, and on to the next question, or the next part of this question. This is B. And it says, under certain conditions, nitrogen reacts with oxygen to make N2O. And you can see here's our equation here. The enthalpy profile diagram for this reaction is shown in figure 5.3. So here's figure 5.3, and it's given us the enthalpy profile. So here's our reactants, and here's our product, and we have some enthalpy values here. And this is the progress of the reaction. So it's calculate, if I just nudge that up just a little bit further. So it's calculate the enthalpy change when 240 decimeters cubed of N2O measured at room temperature and pressure is formed from N2 and O2. Right, so the first thing we need to do is work out the number of moles of N2O. Now, any gas at room temperature and pressure will occupy 1 mole of any gas, will occupy 24 decimeters cubed. But you can see here this is occupying 240 decimeters cubed, so that tells us that N2O is 10 moles of N2O. So I'm just going to put that on there. So moles of N2O would equal 10 moles. Okay, so that's fine. And then we need to work out the enthalpy change. Now the enthalpy change is going to be, if I just pull this down here, this is the enthalpy change here, because there's our reactants and there's our product. So this is the enthalpy change here. So what we're going to do is we're going to do this multiplied by 10, because we've got 10 moles of the stuff. So I'm just going to put this on here. So that's going to be 164 multiplied by 10, and obviously that would equal 1,640. However, as you can see, we are only forming 2 moles of this stuff here. So, well, this is per mole, should I say? So what we have to do, this is 2 moles, sorry, yeah. So this is the value for 2 moles, but we only need 1 mole because it's per mole of substance. So what we have to do is we have to take the 164 we've just worked out, divide that by 2. Now it's really important because this value here is the number of moles for 2 lots of N2O. We only need 1 mole because it's always, that's the definition. So it's 1640 divided by 2, and that should give us 820. And so our enthalpy change is 820 kilojoules, and so that gets us both marks there. So the marks come in by working out obviously the answer, which is 120, and working out the fact that it's 10 moles. That's where you get your 2 marks from. Okay, and if we go on to the next question. So this says, what is the enthalpy change of formation of N2O? So this is in kilojoules per mole. So this is 820. Remember, this is the energy change. We had 10 moles of this, because that's what we just worked out there. So all we have to do is we take the kilojoules bit, which is 820 kilojoules per mole. We have 10 moles of that, and that's going to give us 82 kilojoules per mole for our final answer. Okay, right, on to the next question, and the next part. So what they've done is they very kindly repeated our cycle here again. It's just the same one, it tells you there, repeated. It says the reaction in equation 5.2 is reversible. So there it is there. And calculate the activation energy for the reverse reaction. So the activation energy is basically, if I were to draw a line along here, that is the activation energy. So it's the difference between the products and the, well, in this case, this is the gap here. This is what we're trying to work out. This is the activation energy. So this will actually be a reactant now because we're going backwards to form our products. So this is the activation energy, the difference between this level here, what we started with, and the peak here. So all we have to do is we take that number, this number, sorry, minus that number. So we're just going to write that down in our equation. So this is going to be 447 minus 164, and that should give us, just bring our calculator over, so that's going to be 447 minus 164, and that's going to give us 283 kilojoules per mole. There you go. Okay, and on to the next one. So it's describe and explain using equations how the concentration of ozone in the stratosphere is maintained. So we just have to basically show a reversible reaction. So we'll show how it's depleted first. So we've got ozone, which is O3, and that will actually decompose to form O2 plus O. And the reverse is just going backwards. So this is just going to be O plus O2, and that will form O3. So this is the reaction that occurs, and you can write this as reversible. I've just written it as two separate equations. Now it does say how it's maintained. So the reason why it's maintained is actually because the rate of this happening, which is the decomposition of ozone, equals or is very close to, very similar to, the rate at which it actually is reformed. And that's how we have obviously a maintained level of ozone. So we're just going to put that down in here. So rate of O3 decomposition equals the rate of O3 formation. All right, okay, so we get 2 marks here. So we get 1 mark for actually writing down our equations, which is there, and we get 1 mark for actually stating the effect. So we have to say the rate of O3 decomposition equals the rate of formation. So the words rate there are very, very, very important. They're crucial. All right, okay. And then the last bit for this question, it says in the stratosphere, NO catalyzes the breakdown of ozone. Write 2 equations to show how NO catalyzes this breakdown. So if it's a catalyst, we've got to have NO, it says NO is the catalyst. So we've got to reform it. It's got to be a product of our second stage of our reaction. So it says it's the breakdown of ozone. So this is O3. And this is effectively going to form NO2 plus O2. So you can see we don't have any ozone left now. But this NO2 here, because remember we have to reform our NO back. So this will actually react with oxygen, which was your other product in here. So you can see O2 is formed, and the O is obviously is around as well. So the NO2 reacts with the O, and what that will form is NO. So you reform that back again, plus you get O2. So you get 2 lots of O2 there. But you must form your product here must be reformed because that was your catalyst. So that's a bit of a prompt to help make sure you get the right answer. And obviously oxygen is one of the products of the decomposition because you just worked it out over here. So there's a few hints there as well. So you get 2 marks for that. Obviously it's a mark per equation. So you get 1 mark there and 1 mark there. And so in total that gets you 11 marks. This is basically just, the examiners here are just testing your ability to understand enthalpy and in particular the enthalpy profile, so the diagram. So you've got to make sure you know every little part of the diagram and make sure you can understand it. But that's it. On to the next question. Okay, so this is question 6, and this is looking at mass spectrometry. So mass spectrometry and infrared spectroscopy are used in analysis. The element sulfur exists as molecules Sn. Says the mass spectrum that would be given by a sample of sulfur is shown below. All the sulfur atoms are the same isotope. So you can see that we've got our spectrum there. So state the MZ value of the molecular ion. Now the molecular ion is always the peak furthest right, the most significant peak furthest right. So in this case it's going to be 256. Okay, it says suggest the formula for a molecule of sulfur. Now what we have to do here is we take our periodic table and we find the mass of sulfur, and you can see sulfur is 32.1. We'll just round it to a whole number, which is 32. So all we do is we take the 256, because that's the molecular mass, and we're going to divide that by 32. So here we go, 256, divide that into 32, and that gives us 8. So that tells us that the sulfur is actually 8. So this is going to be S8. Okay, and then it says, for the next question, it says, what is the formula of the fragment ion with MZ128? Now, if we do 256 divided by 128, you can see that this is half as big. So that must mean it's an S4 molecule, because we obviously only have half as many sulfurs. But the crucial thing is it says fragment ion. Now with mass spectrometry, the only ions that go through are positive ions, because that's the only ones that are actually are able to be deflected and detected at the end of the mass spectrometer. So it must have a positive charge as well. You've really got to put that in. Make sure you don't forget that bit. All right, okay. So there's 3 marks straight off. Right, next question. So it says a sample of an element L is analysed using mass spectrometry. The mass spectrum is shown below. You can see they've given us the percentage abundance and the MZ of the different parts of this element, so different isotopes. It says calculate the relative atomic mass of L and give your answer to 1 decimal place. So we're going to make sure our level of precision is correct. All right, okay, so I'll just pull that a bit further down so we can see the table. So what we have to do is we have to work out the molecular mass of this, and all we do is we take the MZ and multiply it by the abundance, and then add all these together, and then we're going to divide them all by 100, because these percentages will add to 100. So this is going to be 194 times by 33 plus 195 times by 34 plus 196 times by 25 plus 198 times by 8. Okay, and if we divide all of that by 100, then we do it by 100 because these are percentages. Just watch out if these numbers aren't percentages and they are numbers such as 3.7 and 10.9. All you do is you add these numbers up and you divide the total of them, your abundance, by whatever that goes there. So because these all add up to 100, it's divided by 100, but just watch out for that. Now, to save time, I've actually done this one already because that will take a while to put in the calculator. And our final answer should come out as 195.2, and you can try that. You put it in your calculator and you should get that. And that's your relative atomic mass of this. So this is 2 marks, 1 for this and 1 for that. Okay, and then on to part C. It says given everyday use for infrared spectroscopy. So an everyday use could be measuring air pollution. There you go. Or you can use breathalyzers as well. So they use them in the police to breathalyze drink drivers, etc. So breathalyzers. So any one of them will do, and you'll get your mark there. All right, okay, and on to the next part of the question. Okay, right, so it says the solvent M is an organic compound used in paints. The solvent M was analysed. M has a relative molecular mass of 72, so we'll use that later on. So the percentage composition by mass of M is carbon is 66.7%, hydrogen is 11.1%, and oxygen is 22.2%. The infrared spectrum of M is shown below, and it's given us the infrared spectrum. Okay, it says the analysis produces several possible organic structures, suggest with reasons two possible structures of M. Right, so what we have to do is we have to work out exactly what this molecule is, and one of the ways we need to do that is working out its empirical formula. So we need to know the ratios of carbons to hydrogens. So what we're going to do is a bit of a hint that we need to work out empirical formulas. They've given us these percentages as well for each of the elements, as you can see on the top there. Okay, so what we're going to do is we're going to write down our elements. Now we know it contains carbon, hydrogen, and oxygen. So what we need to do is to write down the masses of these. Now carbon was 66.7, hydrogen was 11.1, and oxygen was 22.2. Okay, and effectively we need to work out the moles. So we're going to divide all of these numbers by the mass. So the mass of carbon is 12, hydrogen is 1, and oxygen is 16. So if we put them into our calculators, we should get the number of moles. So let's bring this over. So this is going to be 66.7. I'm going to divide that by 12, and that should get us 5.55, but I'll just put 5.56 just to round it up. Okay, and so if we do the rest for the rest of them, obviously 11.1 divided by 1 is just 11.1. And then if we do 22.2, oops, 0.2, divide that by 16, and that should give us 1.38, or around that, it's 1.39. So we're going to put 1.39, which goes on there. Okay, so we're then going to find the smallest number of moles, which in this case is this. I'm going to divide all the numbers by this. So 1.39 is the smallest number, so we're going to divide all of them by 1.39. Okay, so this gives us 1 for the oxygen, 11.1. We're going to divide that by 1.39, and that gets us 7.98. But if we round that up, that will give us 8. So we want whole numbers. And carbon is going to be 5.56. Divide that by 1.39, and that's going to give us 4. Nice round number. Okay. Go. Right. So the formula, as you can see here, would be C4H8O, and actually that has a mass of 72 anyway. So not only is that an empirical formula, but it is also our molecular formula as well. So what we need to do is then need to identify a functional group. So we know the atoms in this molecule. Now we need to identify a functional group. So you can see here we've got this peak here at 3000, and we've got a significant peak here. So what we'll do is we'll look at this peak here, because this is the biggest one. So we'll see what that is. So let's bring in our data table, which is there. Okay, so you can see that this broad peak is probably about 1516, about 1710, roughly around there. So we'll have a look and see if we've got one that fits in within that band. As you can see, we do. There's the 1710 would fit in with this band. So that tells us we've got an aldehyde, ketone, carboxylic acid, ester, or amide. But we've got this carbonyl group here. And that fits in with our formula as well, because we have to have an oxygen, but just one of them. So actually, we actually have, it has a C double bond O absorbance. And this is going to be at roughly about 1710 centimeters or per centimeters. So what we need to do is come up with a formula that has this molecular formula, and it must have a carbonyl group. And there's 3 potential ones here, so I'm going to draw down all 3. Here's your first one. So you could have CH3, CH2, CH2, C double bond O with your hydrogen. So there's one. You could have this structure, which is going to be CH3, CH3 on the top there, C double bond O coming down at the bottom there, and then your hydrogen. So you can see this is a branched version of that one. Or you could have number 3, which is CH3, CH2, C double bond O, CH3. So you can see all of these have the carbonyl group in, and that's the most important thing. And they all have this molecular mass as well. Just be careful you're not drawing the same thing. So you might take this and just flip it back to front. It means the same molecule. You have to draw at least 2. You don't need to draw 3, just 2. Two molecules that are completely different when you actually name them. So that's really important. A lot of people kind of get a little bit confused with that, or they end up just drawing the same molecule but just kind of flip back to front. Right, so in terms of marks, there's 5 marks up for grabs here, so there's quite a few. Now, in terms of the marks, we have 1 mark for working out our ratios there. We also get a mark for working out the formula, the empirical formula, and it just so happens to be the molecular formula as well. You get a mark for stating that we have an absorbance at 710, and this is because of the carbonyl group. And then your last 2 marks come in for drawing your 2 structures. You only need 2 of them. You don't need 3. So you get 1, 2, 3, 4, 5 marks in total, and that's the end of that question. So mass spectrometry. Make sure you're able to do empirical formulas, and make sure you'll be able to read your spectra correctly in order to work out relative atomic mass. That's it. On to the next question. Okay, so this is question 7, and question 7 starts by saying the list shows the structural formula of some halogenoalkanes, and you can see they've given you a range of different types there. So it says choose from the list above the letter of halogenoalkane that is extremely unreactive. All right, so if we look at the range here, the actual one that is extremely unreactive will actually be N, and the reason why is this is actually a CFC. And CFCs are notoriously unreactive, and that's how they can go through the atmosphere without reacting with anything until they get to the top of the atmosphere where there's lots of UV and they break up and they can deplete the ozone. So yeah, N is definitely the most stable, which is the CFC. Okay, and then it says B. It says halogenoalkanes react with hot potassium hydroxide, aqueous, to make alcohols. Choose from the list above the letter of the halogenoalkane which reacts with hot potassium hydroxide to form a diol, a molecule with 2 OH groups. Right, so what we're looking for is a molecule with 2 halogen groups that can be displaced for an OH. So the one with 2 halogens would actually be S. And you can see we've got an I and a Br here. And these are on 2 separate carbons that could react to form a diol. So actually this one would be S. Okay. And then on to the next one, which is part 2. It says, using the curly arrow model, describe the mechanism of the reaction between CH3, CH2, CH2, CH2Br and hot potassium hydroxide to make an alcohol. Include relevant dipoles and the name of the mechanism. Right, so we're going to start by drawing out this molecule here first. So we're going to put CH3, CH2, CH2. Now what I'm going to do is I'm going to separate this one out because this is the one that's going to be involved in the reaction. And this is going to react with potassium hydroxide. So I'm just going to put OH, lone pair, negative charge on there. Right, now the crucial thing is that we have a delta positive and a delta negative there. That's why I've separated this out, because this is where the reaction is going to be. Now our OH minus is actually got a negative charge and a lone pair. And this is effectively going to displace the bromine. So this is going to start and go for that delta positive carbon. You must draw it going from the negative charge or the lone pairs to the delta positive carbon. And this is starting to form a bond with this carbon. So now it has to break a bond because there's 5 bonds on there. It breaks the weakest bond, in this case the CBr. And so the electrons go from the bond to the bromine. And that's really, really important. If you do it from anywhere else, you won't get the mark. Okay. And the product is going to be CH3, CH2, CH2, C, H2, and then you've got OH. And obviously you have your Br minus that's now floating around there because that's just been displaced. Okay, and then it asks for the name of the mechanism. So the name of the mechanism is going to be nucleophilic substitution. This is a nucleophile. This is going for a area of electron well, a deficiency of electrons, which is your delta positive carbon. So this is going to be a nucleophile, so we're going to call this nucleophilic. And this is substitution because we're swapping the bromine for the OH. There we go, nucleophilic substitution. So marks, you would actually get a mark for this arrow, so that's 1 mark there, 1 mark for this arrow, a 1 mark for drawing your final structure, and then 1 mark for your actual name of your mechanism, which is nucleophilic substitution. So make sure your arrows are pointing the right way. That's the key thing. Okay, right, on to the next question, the next part. So part 3 says, why is the reaction of P with hot KOH slower than the reaction of Q with hot KOH? Right, so P is slower than Q. So let's go back and have a look. Here's P and here's Q. And you can see the only difference is the halogen here. So one's bromine and one's iodine. Now it says, why was P, this one, slower than this one, which is with Q? Now the simple answer is that the CI bond is actually weaker than the CBr bond. So because that's weaker, this is easier to pull off and displace with your OH group. So yes, that's your answer. So let's go down and write it down into there. So this is your CI bond is weaker than the CBr bond, and the CI bond is easier to break than CBr bond. All right, okay, so we have obviously 1 mark there, but you have to make sure that you say that the CI bond is weaker than the CBr bond. That's because the iodine atom is a lot bigger, and the attractive forces between the shared electrons in the bond and the nucleus of the iodine is a lot weaker, so therefore the bond is a lot weaker, and therefore it's easier to break. So you need to include both of them points to get that mark there. Okay, right, so on to the next part of the question. So this is the final part of this question. So it says, write one equation using structural formula to show how butene can be converted into one of the listed halogenoalkanes, NOP, QRS, or T. So we're looking for butene. So we need to look for a place where we've got a halogen somewhere in the middle. So if we have a look on here, you can see that R has the halogen, which is this one here, and this halogen is sitting on the second carbon, so that would suggest that we did have a double bond that was sitting somewhere in between this carbon and this carbon. So because you see we've lost the hydrogen there as well. So actually the name of the molecule is actually related to R, and we're going to add HCl because we said that molecule was had a chlorine on it. So it's going to be CH3, CH, CH, CH3. So this is your butene, because there's your double bond that's in there. And it has to be structural formula as well, so it has to be written like that. And that will form CH3, CH2, CH, Cl, CH3. So that was actually, if I just put it back again, that one was actually R there, and you can see there's the chlorine. So we had to use that's the one that was the original molecule, the butene, and that forms this one, which is your 2-chlorobutane. And you get 2 marks for that. You actually get 1 mark for drawing the correct structure, which is this one here, and you get 1 mark for the whole equation. So you get 2 marks, which is pretty generous, I think. Okay, and then on to the last one, which is D. Say CFCs were once used as propellants, but have now been replaced by biodegradable alternatives. Say state one type of a biodegradable alternative. So there's a few here. You could use something like HCFCs. So they're a little bit better, or you could use HFCs. Or you could just use hydrocarbons, which are even better because there is no carbons. because there is no halogens in them whatsoever. So there we go, 10 marks available. Mechanisms are obviously pretty crucial for this. You got the bulk of the marks for mechanisms, but yes, not too bad. Right, on to the last question. Okay, so this is the last question. This is question 8, and it says polypropene nitrile is used to make acrylic fibers for clothing. Polypropene nitrile is a polymer manufactured from propene nitrile. So there's your propene nitrile there, and it asks us to draw a section showing 2 repeat units of polypropene nitrile. So all we have to do is just take out this double bond and put the bonds either side of the carbon. We've just got to show trailing bonds as well, which are the bonds that extend beyond the molecule. So we're just going to draw that there. There's your CN at the top there and your hydrogen. And we have to draw 2 of these. So we'll just repeat the same again. Hydrogen and trailing bond. There you go. There's your first mark. Okay, and then it says explain why this manufacture of polypropene nitrile has a 100% atom economy. So one of the key things is that this is actually an addition reaction because we're opening up the double bond and adding it to form a longer molecule. But you could also say that all the reactants are used to make the product. So that's what we're going to put. Or like you say, you could say addition reaction as well, and they'll actually accept that as a mark. So there's your first 2 marks there. Okay, right. So on to the next part. So this is a 5-mark question, and it says propene nitrile is manufactured from propene as shown in the equation. They've given us an equation here with an enthalpy value. It says the conditions used are 450 degrees Celsius and 2.5 atmospheres in the presence of a catalyst. Describe and explain, using Le Chatelier's principle, the effects on the position of equilibrium of the following changes. So a temperature above 450, a pressure above 2.5 atmospheres, and the absence of a catalyst. And in your answer, you should link the effects you describe with your explanations. Right. So the first thing we're going to do is going to look at the temperature bit first. So we're saying that this temperature is above 450 degrees Celsius. So you can see here that the forward reaction is actually exothermic. So that means if we when we increase the temperature, then the equilibrium will always try and shift to minimize that temperature rise, and it will do that by absorbing energy. So if the forward reaction is exothermic and we're increasing the temperature, then it's going to shift to the left to try and move in the endothermic direction to remove that energy. So we're going to write this down in a proper way. So we're going to say, first of all, we'll state as we increase the temperature, equilibrium will shift to try to minimize the temperature rise by absorbing energy. Okay, so there's one point that we've made there. We also have to state that the forward reaction is exothermic, so we'll put that on there now. So forward reaction is, sorry, exothermic, not endothermic, exothermic. Okay, so, and then we need to say what will happen to equilibrium. So equilibrium will shift to the left in this case, so we'll put that in there. There you go. Equilibrium will shift to the left to reduce temperature. All right, okay, so we've talked about temperature, so now we need to look at the pressure side. And again, we'll just make this comment here. So if we increase the pressure, equilibrium will shift to minimize pressure change by reducing the pressure. Okay, by reducing the pressure. Okay, so that's pretty straightforward. Now, what we've got to do is we've got to, just like we've done with the temperature, if we increase the pressure, which is what we're doing here, equilibrium will try and reduce the pressure, so it will shift to the side with the fewest number of gaseous moles. You can see on the right-hand side, we've got 4 moles on the right, and on the left, we've got 3.5 moles. So equilibrium will again shift to the left to reduce the pressure. So we need to say that increasing pressure shifts equilibrium to the left, which is what we put there, and the reason why is because we have less gas moles on the left. Okay, so we've described temperature, we've described pressure. Now what we have to do is we have to talk about the absence of a catalyst. Now, the good thing with this is actually there isn't much to write about it because a catalyst has no effect on equilibrium. So therefore the absence of a catalyst will have no effect. So we'll put this down here as well. So catalyst has no effect on equilibrium. All it does is it speeds up the rate at which equilibrium is established, but doesn't actually have an effect on equilibrium. Okay, right, so that's 5 marks. The marks come in, they bunch them they bunch the marks quite a lot in this question. So the marks actually come in for stating that one there, and that one's bunched up with the pressure one as well, so that just gets you 1 mark. The forward reactions exothermic, that actually gets you a mark by stating just the forward reactions exothermic. And then also talking about the effect of equilibrium. Equilibrium will shift to the left to reduce the temperature. You've always got to state the effect. That gets to the 3rd mark. The 4th mark is by stating that there is less gas moles on the left-hand side. So that gets to the 4th mark. And then the 5th mark obviously comes in by stating that the catalyst will have no effect on equilibrium. So that's where you got all your 5 marks. Okay, right, on to the next part. It's a big question, that one. Right, so this is question D. It says a factory is able to make 11.13 kilograms of propene nitrile from 220 moles of propene. Calculate the percentage yield of the reaction to form propene nitrile from propene. Right, so what we have to do, with this being a yield, we have to work out what the actual moles are. So we'll just put that in there. This is the actual moles of propene nitrile. So what this is basically just the mass over the MR. So the actual moles that we could possibly collect, or what they are collecting, should I say, is the mass, which is 11.13. Now I'm going to convert that to kilograms. So we're just going to multiply that by 1,000. So that's 11130 grams. And we're going to divide that by the MR. Now the MR of propene nitrile, if we bring this back over here, there it is here. So basically, we're just going to add that up. So that's 12 plus the 2, which is the 2 hydrogens, plus another 12 for the carbon, plus the 1 for the hydrogen there, plus a 12 for the other carbon, and then finally plus 14 for nitrogen. And that's going to give us 53. So just going to come back over here. So I'm just going to stick 53 into there. Okay, and so the actual number of moles propene nitrile is going to be 11130 divided by 53. So the actual number of moles is going to be 210. So we're just going to put that on there. And then to work out percentage, the percentage yield, yeah, we do 210, because this is the actual number of moles, divided by what they got, or what they used, which is 220, and we're going to multiply that by 100. So if we put that in there, there's our 210 already. I'm going to divide that by 220. That will equal, times that by 100, and we get 95.45. So if we round it up, it's 95.5. Okay, so this is going to be 95.5%. Okay, so and the marks come in by saying 210 moles, which is there, and obviously 1 mark for your actual percentage answer as well. Okay, right, and then finally on to the last question, which is E, and it says the chemical industry uses temperature and catalyst to control the rate of reactions using Boltzmann distribution diagrams. Explain the effect on the rate of a reaction of increasing the temperature and adding a catalyst. So we've got to use Boltzmann distribution graphs. So what we're going to do is we're going to draw one of them now. So there you go, there's one there. And we're going to label our axes. So this is going to be energy on the bottom, and this is going to be number of molecules on the side there. Right, we're going to draw our standard distribution here. So draw that up and then make sure it drops nicely back down. Okay, right, so there's one curve there, and this is just a standard one. Now, what it's asking us to do is it's asking us to explain the effects on an increase in temperature. So in terms of that, I'm going to do this one in red. If we increase the temperature, we actually start at 0, 0, because that's where we need to start from there. And the curve actually goes up, but it peaks slightly to the right and is lower than the other one, and actually only crosses the original line once and never actually touches the bottom, but finishes a lot higher. So you've got to make sure it's drawn specifically like that. This is the average temperature of the molecules. So if we increase the temperature, the average energy the molecules have will be higher compared to at a lower temperature, as you can see. And the area under the curves tells us the basically the number of molecules there. So we have more molecules with a higher average energy. That's what this graph is telling us. So we need to label this. It's really good to label these. So I'll put higher energy here, higher temperature, sorry. Temperature. Okay, and we need an activation energy, and this is the energy at which successful collisions can occur. So I'm just going to draw that there. So we'll call this EA for activation energy. And you can see that actually here, any particles in excess of the activation energy will have enough energy for them to have successful collisions. So what we can say is that with a higher temperature, see compared to the lower one, with a higher temperature, we actually have more molecules with energy greater than the activation energy. So that's a key point to actually make. The fact that we've got a higher temperature and we have a lot more particles with a greater activation energy. So that means we get more successful collisions. But we'll talk about that later on when we get there. Okay, so now what we need to do is we also need to make a comment on adding a catalyst as well. And what a catalyst does is when we add it, it actually lowers the activation energy, and we can show that in our on our Boltzmann distribution by adding another line. And we're just going to add one here, and we're going to call this EA cat. So what's happened is effectively we've now got many more molecules that have energy or enough energy to have a successful collision, because the catalyst reduces the activation energy. You can see that it's been shifted to the left. So the total energy has now, or the total area underneath the graph beyond the activation energy is now a lot bigger. So we're going to write that in words. So I'm just going to pull that to one side. Okay. So what we need to say is we need to say adding a catalyst lowers the activation energy. Okay, so that's what we've just described there. Right, now what we have to do is we have to try and describe, in terms of collision theory, what's actually happening with these graphs, because we have got to add a description as well. So what we can say in summary is that the reaction is faster with a catalyst and increased temperature. All right, okay. And then we've got to say that the reason why is because we have many more molecules with energy greater than the activation energy. So we're going to write that down in there as well. So many more molecules with energy greater than the activation energy. Okay, and then obviously after you've done that, we then need to say, well, what effect does that have? Well, it means that we have more successful collisions. So we're going to put that in there as well. So hence, you get more, and it's important to include that word successful as well. So you get more successful collisions. All right, there you go. So let's tot up the marks. There's 7 marks there, which is quite a lot. So I'm just going to quickly go through each one of them. Now you actually get a mark for drawing your distribution. So if I just nudge that up there, you get 1 mark for drawing your distribution correctly. You get 1 mark for labeling it properly. You also get 1 mark for drawing your other curve showing a higher temperature, and it must be flatter, and the peak must be further to the right if it's of a higher temperature. And this curve must be above that, so it must be exactly like that. They're the features. It must start at 0, 0, must only cross this line once, so little features like that. So you get a mark for all of that, and obviously talking about the activation energy as well. You get 1 mark for talking about adding a catalyst lower on the activation energy, so you need to draw another EA for catalysts and labeling it, and this is your mark here. So far we've got 1, 2, 3, 4 marks, which is there. There you go. So you get 1 there. And then your 5th mark comes in by saying this point, that the reaction is faster with the catalyst and temperature. The 6th mark for saying that many more molecules have energy greater than the activation energy, and then therefore you get more successful collisions if that happens. So that gets you these 7 marks in total. So there you go. Make sure you are really specific and you are covering all points, and you are constantly saying why this happens. So you're saying, what is it that's happening, and then why is it? So make sure you explain it, because that's what they're looking for. Lots of extra marks there, and make sure you give enough points to get the 7 marks that's required. And all you have to do is just make sure you read that question very, very carefully. But that's it. That's the end of the paper. Bye-bye.